Okay, so in this video I thought it would be fun to take a look at a likelihood ratio test in a specific example. So we're going to suppose that we have a normal population with an unknown variance, and we want to check a null hypothesis that the mean has a certain value. Okay, and we're just going to try to come into this with an open mind and use the likelihood ratio strategy to come up with a statistic that we could use to test our hypothesis with. So what's the plot here? We're looking for a statistic to use to test our hypothesis, and hopefully for some critical region as well. So recall that if we have a normally distributed variable with a known variance, then previously we found that the sample mean was the statistic that the likelihood ratio test suggests. And the intervals that we get from the likelihood ratio test have the form of the absolute value of the difference between the sample mean and the hypothetical mean mu naught should be no bigger than some particular value k, and then we solve for that value k. Or, I'm sorry, the critical region is when it's bigger than some particular value k, when it's sufficiently far. Okay, so, but what do we expect to happen when we don't know the population variance? So we can still go ahead and crank it through the likelihood ratio test and see what we get, and that's what we're going to do today. But the punchline will be that it turns out that in this case the likelihood ratio test suggests a familiar statistic that we've seen before, the t-distributed random variable that you get by taking the sample mean minus the hypothetical mean quantity squared divided by the sample standard deviation over root n. So this is the t random variable with n minus 1 degrees of freedom that we saw once before. And so in this video, we're going to just take a look and see how that comes about from the likelihood ratio test. So just to be clear, we have the null hypothesis that the mean has some value mu naught, the alternative hypothesis that it doesn't have that value. And here we're supposing that our density function, function of x1 through xn, is looks like 1 over square root of 2 pi sigma squared. We have n independent observations, so that's going to go to the power n, e to the minus 1 over 2 sigma squared, sum of your xi's minus mu squared. Okay, so that's the animal that we're looking at. And of course, if we, in this thing, this is not really just a function of x1 through xn, but it also has our unknown parameters, which we could explicitly write there if we want to. Or depending on how we're thinking about things, we might simply write this with the variables reversed, thinking of this as a function of the variance and the mean, and thinking about these numbers as constants for the moment, and this is called the likelihood function. That's what we're going to be dealing with. And so if you remember, we for our estimator lambda is going to have the form of taking the maximum over sigma squared and mu such that the null hypothesis is true of this likelihood, divided by the maximum over unrestricted sigma squared and mu, all sigma squared and mu, so to speak, L of sigma squared mu x. Strictly speaking, it's the sigma squared and mu that are eligible for consideration under either hypothesis. So let's see how we would maximize that. So we can do a little bit of a simplification, I guess. So if we write our function L of sigma squared and mu on my x, let me not copy it down. Let me just grab it right here. Okay, so there we are. So, we can kind of maximize it with respect to kind of either variable. So let's kind of, for example, if we hold sigma squared fixed and we let mu vary, then we can see what's the maximum value for, that we get for a given sigma squared if we let mu vary. And similarly, if we hold mu fixed and let sigma squared vary, then we can maximize that. Let's go ahead and do at least one of those. So in both cases, we'll use the strategy that the maximum value that this L takes is going to happen at the maximum value of its logarithm, right? So we can, instead of maximize this thing, we'll maximize the logarithm. It's a nice monotonically increasing function, so that works just as well. So if we go ahead and take that logarithm, so if we look at ln of L of sigma squared mu x, what do we got? So all this stuff combines to 2 pi sigma squared to the minus n halves power. So I get minus n halves times the logarithm of 2 pi plus the logarithm of sigma squared. So I get that from my first part. And my second part, I am subtracting, 1 over 2 sigma squared, sum of xi minus mu squared. Okay. So now, for example, if we wanted to maximize this with respect to mu, we'd look at the partial derivative with respect to mu of this and set that equal to 0. So if you do that, you can see that all this stuff is just a constant with respect to that. We really just have action going on there. And what do we get? We get minus 1 over sigma squared, that the 2 kind of kills that other 2, sum of xi minus mu times the derivative of the inside, which is that. If we're going to set this thing equal to 0, then that's going to tell us that the sum of the xi's is equal to the sum of mu from 1 to n, which is n times mu. And that says that the maximum is going to happen at 1/nth the sum of the xi's. Or in other words, this thing is x bar. So max at mu equals the sample mean. Let's suppose we wanted to optimize this or maximize this with respect to the sigma squared. So for that, I'll take d by d sigma squared. I mean, I know that looks a little funny, but sigma squared I'm just treating as a variable. You could maybe substitute sigma squared equals tau and take the derivative with respect to tau if we wanted to. I could have done it with respect to sigma, but whatever, I'll just do it with respect to sigma squared. And right, so this first part then gives me a 0, and I have this minus 2 sigma squared there. Let me just say that this is, so what is this? This is a d by d sigma squared of minus n over 2 ln of 2 pi, just rewrite it for a moment, ln of sigma squared minus 2 sigma squared to the minus 1 power, the sum of xi minus mu squared, or I can pull that, what did I just call it like that, for example. Okay. So then when I go ahead and take that derivative, okay, so again, this first part goes away. The ln gives me, so I still have this minus n over 2, and then I have times 1 over sigma squared. So it happens with the logarithm derivative thing. And then for this part, the minus 1 comes down, turns into a minus 2, and so I get a minus 1 over the minus comes down, makes that a plus, 2 sigma squared squared, sigma to the 4th, and then times the sum of the xi's minus mu squared. Okay, so now if we're setting this thing equal to 0, we can do that by multiplying by 2 sigma to the 4th to clear the denominator, by moving this piece over to the other side, and then seeing what we get. So what do we have? We get what? We got that sigma, the sum of xi minus mu squared is going to be, so let's see, plus, or no, divided by plus, so n multiplied by sigma to the 4th, I get a sigma squared, so I get that. that's my solution, or in other words, I get that sigma squared, the value for sigma squared is 1 over, the sum of the xi squared, xi minus mu squared divided by n. So what is that? That's not the sample mean, right, which would have been dividing by n minus 1, but this is actually what we could call, not the sample variance, but this is the what we could call sigma squared hat. It's the maximum likelihood estimator for the variance, if you remember. So okay, so that's what we get. We get that. Let's see. This is the it's the estimator that we get for the moment for that second moment around 0. Okay. So altogether, we know that. Let me just kind of gather that information. So when mu varies, the max will happen at mu equals x bar, and when mu is fixed and sigma squared varies, max happens at sigma squared is equal to this MLE estimator with respect to that given kind of mu as the actual mean there. Okay, the maximum happens there. Okay, so then let's then go ahead and say that if we're going to look at this lambda, which is going to be the max where under the null hypothesis, so the null hypothesis, mu equals mu naught, and sigma squared varies just in a positive number of this L of sigma squared mu x divided by the max over whatever values we want. Sigma squared is still positive, of course. L of sigma squared mu x, so that's what we're looking at. And what do we got? We got that in the top, mu is mu naught, and sigma squared is this thing for that given mu, so it looks like sum of the xi's minus mu naught squared over n, mu naught x, and then on the bottom we get this for right. So the main point is that in the top mu is fixed. Mu is fixed to be mu naught, and so this is fixed. And then we have, once mu is fixed, the sigma squared maximum happens at this value for that given mu. And on the bottom, the mu is the x bar, and so we get xi minus x bar over. And I guess this is really what we had for the MLE estimator for the variance. Okay. Okay. In any case, so moving right along. Okay, so we get that where L again is this animal right here. And so what do we got? We got lambda is how lazy can I be? Let me not be lazy. Let me just go ahead and actually do this. So what do we have in the top? We have 1 over, let me put the whole thing to the n over 2 this time. So we have 1 over 2 pi, the sigma squared. So the sigma squared for the bottom is the sum of the xi minus mu naught quantity squared over n. E to the minus 1 over 2 sigma squared. Sigma squared in this case is the sum of the xi minus mu naught over n, mu naught squared over n. Yes, that looks right. Okay. Times the sum of the x minus the minus mu, and what is mu? It's the mu naught in this case in the null hypothesis land, squared, Yeah, that's my top. Oh, and this whole thing is to the power n halves. Similarly, in the bottom, I have 1 over 2 pi. Hold on to your hats, you guys. We're going to get through this. We're going to get through this. Okay. Xi minus x bar squared. So I'm just going ahead and I'm plugging in this guy for my sigma squared over n. All that is to the n halves power. And then it's e to the minus 1 over twice the sigma squared for that, which is this sum of xi minus the x bar quantity squared over n times the sum of x minus x bar x. These are xi's. Right. Okay. Good. So we've got that. Now you'll notice we have a bit of cancellation going on here. So this term here is the same as this term there, which is in the denominator. And this term here is like this term here in that denominator. And so those guys actually cancel, and in both cases, and then that n flips. So both of those are just really e to the n over 2's, actually. So we just get lambda is, oh, and of course, on the bottom, these fractions, I can kind of flip these fractions around. So I get a 2 pi times the, let me go ahead and like, I'll stick this in up there and this in up there, but then the n's cancel actually. So I get a 2 pi sum of the xi's minus x bars quantity squared over 2 pi sum of xi minus mu naught quantity squared. Of course, all that's, you're going to get a lot of cancellations there. And then, and all that is to the n over 2. And, and on the outside, we have some stuff that's now going to cancel. It's just an e to the minus n over 2 over e to the minus n over 2. Okay, it's getting a little better. So what is that? We, again, get a bunch of cancellation. We really just have the sum of xi minus x bar squared over the sum of xi minus mu naught quantity squared to the power of n over 2. Okay. Let's take a breath. Let's take a breath. All right. This is the lambda. We're not done yet. We're not done yet. Okay. There's a handy formula that comes up a bit. When you're playing with these things, and that this nice formula. There's a few different ways to kind of express it. It's that if I take a sum of these xi's minus x bar squareds, and I subtract off the same kind of sum with the mu, with the actual mean, or just any number really. The important thing is that this should be the Sale mean, the average of the xi's. If I do this subtraction, then what I get is n times x bar minus mu naught quantity squared. Okay, this is just a bit of algebra. It's just a matter of just distributing, grouping terms, and using the fact that the sum of the, so you do some algebra, you distribute, group terms, and use the fact that if you add up the xi's, you get n times x bar, and you just do that, and you eventually get that. Okay, so I'm just gonna not work that out right now, but that's a handy formula that will let us kind of simplify what we have here, because I can write this. So how am I going to use that? I'm going to rewrite my denominator. I get this divided by, let's see, so if I move this term to that side and this term back here, using mu as mu naught, I would get, what would I get? The sum of the xi's minus x bar squared plus n times x bar minus mu naught squared. All that to the n over 2 power. Okay, let us continue. So lambda is that, but I can, the thing about this fraction is like these guys are the same, and so you'd like to kind of cancel them but you could do that if the fraction was upside down, right? If that fraction was upside down, then it would be 1 plus the other ratio. So to make it upside down, I'm just going to flip it and write this whole thing as like this whole thing is 1 over what I have there. It's like forcing it, but it's okay. Like this thing at the bottom. And now I can kind of break that up. So this is 1 over 1 plus n times x bar minus mu naught squared over the sum of the xi's minus x bar squareds. Okay. And so now let me kind of rewrite this a little bit. We're getting there. We're getting there. Now I'm going to rewrite this a little bit to get some more familiar players on the scene. If I pull out an n and an n minus 1 that wasn't actually there, then what am I left with? I'm left with, I pulled out that n. I'm left with this x bar minus mu naught squared over the sum of the of the xi's minus x bar squared over n minus 1. Okay, so what does that look like? This is 1 over 1 plus this constant times x bar minus mu naught squared divided by the sample variance. Okay, and now we're basically home free. I guess what do I need to do? I need to I guess I should have stuck in another term. So I have an n minus 1, or I want to stick in 1 over root n in the bottom, so I'd multiply by a root n on the bottom, which I guess means I need a root n there. Yeah, okay, that's what I have, right? So I get it looking like that instead, and then I have x bar minus mu naught squared. And now, what's the deal? So this is my lambda. If I call this variable, I don't know, like maybe I'll call this t. If I call that variable t, maybe I should call it lowercase t, and that s should really be a lowercase s, I guess. This is the measured value of my sample variance. Then what I get is, so this lambda is 1 over 1 plus root n over n minus 1 t. And so what does my test then end up looking like? So the test is, or the critical region is, I'm going to throw out my null hypothesis when my lambda, which is kind of the relative likeliness of my null hypothesis, is too small. So it's going to look like that. This tells me reject H naught if this is my critical region. And in other words, it has the shape 1 over 1 plus root n over n minus 1 t less than or equal to k. Or in other words, if I move that around, 1 over k less than or equal to 1 plus root n over n minus 1 t, or in other words, t bigger than or equal to 1 over k minus 1 times n minus 1 over root n. Which, I don't know, we could just call like some other big k. And so, in other words, my critical region has the shape of saying, the standard variable that we use for the t distribution should be at least k, right? So this t, remember, was what? X bar minus mu naught squared over s squared divided by root n. And this is a variable with a t distribution, or the random variable where everything is uppercase is the variable with the t distribution. So our hypothesis test has the form, if the if this t value, if this random variable t is bigger than or equal to k, then we reject. So what we end up getting is so this is a t distributed random variable with n minus 1 degrees of freedom, and so we can then build intervals for those just in the same way that we've done before.